Hello everybody, you're very welcome to this episode of Programming and Algorithms. In this episode we're going to look at how insertion sort is implemented. So in plain English, insertion sort works as follows. You take the first two elements of the list and you sort them. Then you take the third one and sort that into the first two. Then you take the fourth one and sort that into the first three, and so on. So if we want to take an example, let's have a look at our array. So our array, the first two elements are out of sequence. So we need to put the smallest element in its correct position and move it back there. Now the first two elements are sorted. So let's look at the third element. It's not in the correct sequence, so we need to move it so it's in its correct position. Now we take the fourth element and we look at where it is and where should it be. It goes all the way across there. Now we take the fifth element, number 16, and it gets moved to the very start of the list. Now that's a big move. It goes all the way across, spans the whole length of the array. We'll see how we do that in a minute. We take the next element, it's 54, and it's in its correct position, so we don't need to do anything with it. The next element is 34, and it has to go all the way over there, and again it's a big move across. And then the last element, 18, has the biggest move. It spans almost the entire array to get moved to its correct position. But the logic is quite simple. We take the first pair of elements, sort them, then the element succeeding the sorted pair, sort that in, then the next element, sort it in. So that's the array all sorted now. So in terms of how we move the elements to the correct position, I'm going to give that a name. We'll call it the insertion sort move, and here's how it works. Let's say if we're moving 34 to its correct position, we have a variable called current, and we store 34 in that variable. Then what we do is fairly straightforward. We move the number 54 into the location that 34 is in. So 54 is in both locations. Then we take 44 and put that into the location that 54 was in. Then we move 42 into the position that 44 was in. And then we know that's where 34 needs to go. So we write 34 into location 3, the fourth element of the list. So that's how we do the move. And I want us to remember that, the insertion sort move, because what that means is if I'm moving from the start of the array to the end of the array, or from the end to the start, I have to move through each element in the list. And whereas for an 8-element array, that's not a big deal. If we're looking at an array that has thousands of elements in it, shifting each element across is actually expensive enough. But that's how we do an insertion sort move. So as we know, the new element, which is called current, how we know if that's in its correct position already is if we compare it to current minus 1. If we think about it, the sorted sublist keeps growing from the left, so that means we have the sorted sublist and the next element to be added in. If we compare the next element to be added in just to the element right before it, which is at the top of the sorted sublist, then if the next element is bigger than the top of the sorted sublist, then we know that that element can be added into its current position. It's sorted already, as was the case with 54. So we just need to compare current with current minus 1, which is, current minus 1 is the end of the sorted bit. So if we compare current with current minus 1, if they're in the correct order, great. If they're not in the correct order, then we move current into current minus 1, and maybe we move current minus 1 into current minus 2, current minus 2 into current minus 3, depending how we go. So before we look at the pseudocode, let's look at it in structured English. So what do we do for each element in the list? From the second to the end of the list, we sort in pairs. So the first two elements are sorted first. Remember what the current position is and the current value. Then, assuming that the previous element is bigger than the current element, let's loop around, and while that is the case, move the previous element into the current position. As we saw, that's our insertion sort move. And then when we've reached the position in the list where current should be, we put it in there. So we keep shifting across until we've got the current value in the position it should be in. We keep doing that in a for loop for the second to the end of the list. So if there's 100 elements in the list, let's say the for loop is approximately 100 times and the while loop is approximately 100 times as well. So to execute this, it's 100 by 100, it's 10,000 times. Or if there's n elements in the list, it's order n squared. So let's look at our pseudocode. So our pseudocode is insertion sort, declare our array, then for 1 to n, and we know for a 0 indexed array, 1 is the second element of the list. So we assign current to be the first value in the array. Now the first value might be higher or lower, we don't know, but it's the first value anyway at the moment. And we remember its position using a variable called pos. If we move the current value down the list and we reach the end of the list, the 0th element, then we know we can stop. We know if the value right beside the current value right beside the sort sublist is smaller than every value in the sublist, then it goes into first position, so we stop there. So our loop has two conditions. While position is greater than 0, and all we're saying there is if we bring the current value to the start of the list, stick it in there, and as long as the value in the position -1 is bigger than the current value. So we keep moving it back, and then we do the insertion sort move by saying the value in the current position gets the value of the previous position as well. So we saw 44 got 44, 42 became 42, 34 became 34, and so on. And we decrement the position counter. And then we save, as we saw with the insertion sort, when we get to the correct position in the array, we write array pos into the current value. So here we go, here's the complexity. Our best case scenario, if the array is almost sorted already, insertion sort will take n attempts. So if the array is 100 elements long, it'll take 100 swaps. If the array is 10 elements long, it'll take 10 swaps. On average though, for a roughly ordered array, our complexity is n squared. So as I said, for 100 elements, chances are it's 10,000. And for a completely messed up array, our worst case scenario is also order n squared. So that's insertion sort. Thanks very much. We'll see you on the next episode.